Hello everybody. In this lecture I'm going to go through measuring radioactivity, and also I will show you a couple of formulas, and through those formula we can get idea about how long it's going to take for one isotope to go through decay and what's the mass after a specific time. But as I started the lecture with devices that we use to measure the radioactivity. So I go with this. That's we're gonna talk about radioactivity. And radioactivity by itself is equal to number of decay events per unit of time. So we're talking about number of decay per time. Okay. And as we show this one, usually the radioactivity we show it by A, and common unit for it is becquerel. And this one is named after, I believe, Henry becquerel. 1 becquerel, okay, one curie. I'm going to talk about this one. 1 curie is equal to 3.70 multiply 10 to the power of 10 becquerel, and this one is equal to 3.70 multiply 10 to the power of 10, and here the unit is going to be decay even per second. So if we want to define the becquerel is going to be equal to one decay, technically one decay event per second. That's gonna be the becquerel. So from now I'm gonna use this unit and try to connect them to mass or rate of reaction. So we know that we have Curie unit, we have a becquerel, and the Curie unit came after Marie and Pierre Curie, and is way bigger than the becquerel, and this is the common unit that we use. Okay, so for now let's focus on devices that we use to measure this radioactivity, and I go with 2 devices that we use a lot, and the first one is gonna be the Geiger-Müller counter, and the second it will be the scintillation counter. The Geiger-Müller counter is a tube, and this tube here, it has a place for particles to get in, and here we have like a kind of a pin. This pin, it will be the cathode, sorry, I meant the anode, not the cathode. This one is the anode. Okay, so the anode one here has a positive charge, and cathode will be this one. So what will happen, like you will have a particles, let's say alpha, beta, or whatever is coming to this, this tube. And when they get in, they will face argon atoms. Okay, so those are argon atoms. And in the gas phase, when they hit the argon, they will generate two particles. Argon plus high energy, and I'm going to show it by here, energy, which is equal to h nu. What we will get is going to be argon plus an electron. So we will have argon with a positive charge, and we will have electrons. Electrons will get close to the one that is positive. They get close to the cathode, the anode. And the argon with positive charge, they move outside, or so to the side of the container. So now what we have, you can assume, like, you have a beaker, and inside that beaker you have a solution. You dip two electrodes in it, and let's say you connect them to each other. If you want to have a conductivity, see something here, you need to have some ions here to transfer the electron. So we need to have some ions to carry the electrons in these directions. And we said we need to have stuff with positive charge, let's say calcium with a plus charge, and we need to have something with negative charge, and let's say chloride with negative charge. So here, in reality, what we are doing, we are building kind of like a cell or electrochemical cell. And the way we generate it, we let the alpha particle or any particle with high energy to get in. When they get in, they will ionize argon. So argon will transfer to argon plus an electron. Argon plus moves to the side. The side, it has negative charge. So here on the shell, we put negative charge, and the electrons move to this pin. So now we will have conductivity. And what we do, we connect, like here, let's say this one, we will connect it to the negative side of the battery. So let's assume I have a battery here, and this is the negative side of the battery. I will connect it here. So this is our battery, and the positive one, if this one is a positive, we will connect it here. And somewhere between the battery and this device, I can put the amplifier to sense this current, and the amplifier, I can put it here. So let's say I put my amplifier there, and the amplifier is going to tell me that how much current I have. If the current is high, that means I get too much radiation, and I need to be aware or get far from that object. This is one this is one device or one type device, like the counter devices that we use to measure conductivity. And usually when you use this device and you put it close to radioactive compound, you will hear a noise of like old radios, like when you try to tune them and get the right frequency. And that noise actually coming from the collision of the electrons with this electrode. And if you get more of those electrons around it, you will hear louder noise. So this is one type of the detector that we use, or counter that we use to track radioactivity. And the second detector that we use, it will be the scintillation detector. Or scintillation counter. A scintillation counter, we have a box. That box, we call it scintillator. Inside this box, we can use sodium iodide. You can use cesium iodide. It depends what you want to track, whether you want to go with alpha or beta, gamma. You change the composition here. So let's say we have huge energy coming to this, and sodium iodide or cesium iodide, it will get that energy, and it will get the energy, and it will shoot it, or it will emit it with light with lower energy. Okay. So I'm going to say here I'm dealing with high energy, and those are low energy. Okay. Right after this insulator, we will put something that we call it photocathode. So this one is going to be the photocathode. The photocathode, it will get those energy, it will get this wavelength or whatever coming to it, and it will eject one electron. So I'm going to go from the beginning. I start with high energy. There is radiation. Radiation is coming to the scintillator. Okay, so scintillator, my bad. Coming to the scintillator. And the scintillator, it will get the energy. It will go to a higher level, and then it will relax, and it will emit some energy. So what here? We have electron went to a higher level. Now it's there. When it's relaxing, when it's going back, it will emit energy. And this energy is less than the initial one. So if you call this one E1 and call this one E2, E2 is smaller than E1. So E2 is here. E2, it will hit the photocathode. The photocathode, it will generate electron for us. Okay, it will this time release electron, and this electron, it will do the job for us. we put something here that is similar to lens. It will focus actually the ejected electrons to somewhere. So we will have a curved area here. Let's say first electron got ejected and this electron is going to go there. So we have electron. And the electron, it will hit this surface. Okay. What is it? This one is secondary. Sorry, it's going to be diode. Okay. A diode, it will get this electron. An electron is coming with energy. It will release a new electron, and also it will reflect this electron to somewhere else. And we will put one in front of it here, like there. So now we have only one electron came to the first diode, and this diode is gonna reflect the electron in this position, this here place, or this diode. And also I said it will release another electron. So now I have two electrons. Okay. What's the reason for, like sending electron in this direction? We give actual voltage for each of these diodes. This one, let's say it has 100 volt. This one is going to be 200 volt. Because of the voltage between them, electrons will move to this side because it has higher voltage. Okay, so we started with one electron, we got two electrons. I will put another one there, here, one there, and I keep playing. Okay. But see what will happen. We started with one, we got two. Number one, it will go there. This is number one. And it will go there, here. Again, it's still number one. Okay. But check number two. Number two, when it will hit here, this is number two, it will get there. That's number two. And also it will eject another electron as well in the number one. So now we will have one electron ejected by number one. This is going to be number three, and one by number two, and that's going to be electron number four. And electron number one is going to go there. It will get here. So that is electron number one, and also it will eject one electron. Electron number two, it goes there, here, and it will eject another electron. Number three, here is number three, got here, and it will eject another electron. I started with only one electron, but check here. Now I have 1, 2, 3, 4, 5, 6 electrons. And if you increase number of the diodes, you will get a really huge number of electrons. And again, every time I go down and increase the voltage, this one is going to be 300, here 400, that one 500, and this one is going to be 600. And each of these diodes is connected to a pin. So here, and same story there. So this one is gonna be number one here. Okay, and all those electrons, all these electrons at the end, they will reach a surface here. They will be taken by this plate, and now we can hook this one, to amplifier and track, how much actually current we got. The more electrons we get, the higher current we will see. Okay, and this is really nice actually, counter. And again, it depends what we use here. We can track different, particles. And you have to be aware that, like, if you change the composition, that means you change the gap between, the level of energies. And if you change the level of gap between them, then the emission wavelength of the emission, it can go up and down. And that means you can, eject higher or lower number of electrons from this photo cathode. Okay, so now I showed you actually two counters that you can use them to track the radioactivity. Okay, so next thing that I'm gonna focus on it is gonna be the radioactivity. I said the radioactivity is gonna be number of decades per second, and the becquerel unit for it is gonna be equal to 1 decade per second. We can use a Curie unit, but it's way bigger than the becquerel unit, and is equal to 3.7 multiplied 10 to the power of 10. Okay, let's focus on radioactivity, and I go with this one. Rate is equal to K multiply R. And here we're talking about, rate of a reaction. K is rate constant, and R means concentration of reactant. Okay. And again, radioactivity, we can show it by A. Radioactivity is going to be equal to K, rate constant, multiply N. And what's the N? N is equal to number of atoms. Okay. This is a first order reaction. First order reaction, and rate of the reaction directly subject to concentration of the reactant. If you increase this one, if you double the concentration of the reactant, rate, it will be 2 times faster because it's a first order. And formula that we use for it is equal to, it's gonna be, I go with N equal to N0 multiply e to the power of minus kt. Okay. Why I'm writing this formula for it? Because even for first order reaction, you go here with time, and this one use activity. You will see that the rate of the decay over time, it will go down like that. A reason for it is it's not going to be linear. The reason for it is like, over time you're going to lose some of the reactants, or number of atoms, because you will not have enough from the reactant or number of or the atoms, rate is going to go down. Okay, but again, it's not going to be a linear one. So that's the reason I use this formula for it. Now, if I get like, natural log from it, natural log it will give me ln of n equal to ln of n0 minus kt. And if you rearrange this formula, you will get ln of n0 minus ln of n equal to kt. So this one is going to be equal to ln of n0 divided by n equal to kt. Okay. And this is first order. Okay, first order formula. So we got ln of n0 divided by n equal to kt. If you are Chem 1515 students, you might say, how come you're writing ln of n0 instead of n? And you might go with this one, ln of n equal to minus kt plus ln of n0. True, but if you you have to keep in your mind that if you subtract minus ln from both sides, what we will get, this one will be 0 minus kt plus ln of n minus n0 minus ln of n. So kt, this time add kt to both sides. You will get kt equal to ln of n0 minus ln of n. And kt is going to be equal to ln of n0 divided, so my bad, this is n. Okay, which is the same formula that I got there. Okay, so this is first order reaction, and here's the formula for it. Now, if you have the first order formula, you can easily calculate the half-life for it. And the half-life formula, we show it by T1/2. So this one is half-life formula. Okay. Half-life formula. And we define the half-life formula, we go with this. We go with is the time that we need to spend, to drop initial concentration to half. Initial concentration to half. So initial concentration, it will be half. Okay. Whatever you started with, it will be half at the end. So that means after this T, after T concentration is going to be half of initial concentration. Okay. So the concentration after this T, it will be half of initial concentration. So wherever you have A, replace it by half of A0, or wherever you have N, replace it by half of N0. So I'm going to go with this one. The formula says ln of N0 divided by N is equal to KT. half-life is equal to time that I need to spend to make the final concentration n equal to half of n0. Wherever you have n, replace it by half of n0. So I go ln of n0 divided by half of n0 equal to kt. So you cancel n0 by n0, and we get ln of 2 equal to kt. And we said t is the half-life. Let's give it name. So I'm going to call it half-life. Okay. So t half-life is going to be equal to ln of 2 divided by k. Ln of 2 is a constant number, and k is the rate constant. So that means half-life that you need, or the time that you need to spend to drop the concentration or number of atoms or molecule atoms in this case to initial one, is not subject to the initial concentration. It doesn't matter whether you start with 2 or 3 atoms or a million of them. Half-life is going to be same for both, because you have ln of 2 is a constant number divided by a constant number, and it depends the unit of k. You can get second or 1/2 here. T half-life, this one ln of 2 does not have any unit, so technically you go 1 divided by unit for k, and unit for k, it can be second minus 1, or say minute minus 1, or maybe year minus 1. Okay. So it depends the unit of k. You will get second, minute, or year. Okay, let's do one example about this one, so then we can understand, how to use actually the formulas. Okay, half-life for carbon 14, and is equal to T half-life equal to 5730 years. Okay. So now find k. We need to figure k. So we get T half-life equal to ln of 2 divided by k. So k is going to be equal to ln of 2 divided by T half-life. Ln of 2 is equal to 0.693 divided by we have half-life, we said, is 5730 year. The answer is going to be 1.21 multiplied 10 to the power of minus 4 year power of minus 1. Okay. Next question is going to be, we know we have this formula for half-life, and also we have ln of n0 divided by n equal to kt. Okay. So the question is going to be, there is a piece of cloth that we found it, let's say, somewhere in US. And what we did, we burned it. We burned not entire of the cloth, we burned a piece of the cloth, and we burned it to carbon dioxide. So burn to carbon dioxide, and then we got the ratio of carbon 14 over carbon 12, and the ratio is equal to 0.25. Okay, so now the question is going to be, how old is the cloth? I need to say one thing. Carbon 12 is stable, and it will stay as it is. But carbon 14 is not, and over time it will turn to either carbon 12 or other, it depends which reaction is involved in it. It can get to something else. Okay, so this one, it goes under decay. This one is not, carbon 14 is not isotope, it's not stable. Okay, so they give me do I have the half-life here? Okay, it's a first order. Because it's a first order, I can go with T 1 over 2 equal to ln of 2 over K. And this one is like, okay, I have the, from the first question, I have the half-life for carbon 14 is given. So I'm going to use this number again and calculate the K. And we got the K here actually. So I can use this K, put in this formula, and try to calculate the time. Okay. So from first question, it was carbon 14. And because it's a carbon 14, we calculated the rate constant for it. We said the T half-life is equal to 5730. We got the K, so we have the K. We can use it again. Put the half-life here, calculate K, and it's going to be again similar to this, same as this number. And use this time the second formula and calculate N. The T. So I go with K is equal to 1.21 multiplied 10 to the power of minus 4 year. Okay. They are telling us the ratio of carbon 14 over carbon 12 is equal to 0.25. 0.25, or you can say, or 25%. Okay, 25%. So we can go either one. Okay, because the question is telling us, is it 0.12 or 25%? Okay, and again, carbon 12 is stable. Okay, so I go with this. Go ln of N0 divided by N equal to KT. Let's find T. T is going to be equal to ln of N0 divided by N, and hold this one, divide by K. Now, ln of, what's the N0? N0, if you started with, 100%, you started with 100%, right now is 25%. Or if you started with 1, right now is 0.25. Okay, 0.25. So the ratio is going to be at the beginning it was either 1 or 100. It doesn't matter which one you are using. If you use 100, then use 25 for n. If you use 1 for n0, then use 0.25. So I use 1 for n0, and then this one will be 0.25 divided by k, which is 1.21 multiplied 10 to the power of minus 4 year minus 1. Answer, it will be equal to 11,500 year. Okay. That's the time that we need to spend. Sorry, this is gonna be the time. Okay, and time here is telling us, you know, the age of that cloth. So how old is the cloth? It will be 11,500 year. Okay, 11,500 year. Okay, cool. So now we practice actually how to use those two formulas. We can do more questions. Okay, let's do one question more and practice the half-life formula. So the question is gonna be, we have radium (223), and we show it by here 223 Ra, and the mass is equal to 1.00 microgram of radium 223, and the T half-life is equal to 11.4 day. Okay, so another question is gonna be find A, and what's the A? A is the radioactivity. Okay, find this one, and find A in becquerel unit and also Curie unit. We go with this. A equal to K multiply N, and K is equal to rate constant it has unit of S minus 1. Okay, for first order unit it will be minus 1. Okay, and we are talking about decay of a radioactive compound is a first order. So if you want to be precise, you have to say unit is gonna be decades events, how many decades are happening for one atom in 1 second. So again, it's going to be S minus 1, but to make it, you know, more clear, we should say number of decades for one atom in 1 second, and N is the number of atoms. So look what we need. We need to find K, and K must be in second unit. Next, we need to know N, and N must be number of atoms. Right now, we have the T half-life in day, so we have to transfer day to to second. Next thing, we have mass in microgram. We need to transfer it to mole, and mole to number of atoms. So let's go with this. We go with T half-life equal to 11.4 day, and 1 day equal to 24 hour, and 1 hour equal to 60 minutes, and 60 minutes, sorry, 1 minute, 1 minute equal to 60 seconds. So T half-life is going to be 9.85 multiplied 10 to the power of 5 seconds. Cool, we got it in second. Next, let's find K. K, we go with T half-life equal to ln of 2 divided by K. So K will be ln of 2 divided by T half-life K will be equal to 7.04 multiplied 10 to the power of minus 7, 1 over second, which is equal to 7.04 multiplied 10 to the power of minus 7 decay. Even for 1 atom in 1 second. Okay. Now, how many atoms we have? And we have 1 microgram of radium 223, 1 million microgram of any compound like radium 223 is going to be equal to 1 gram of radium 223, and 223 gram of radium is going to be equal to 1 mole, and 1 mole is equal to the Avogadro number. So the answer is going to be, we have 2.70 multiplied 10 to the power of 15 atoms. Okay, cool. We got the number of atoms. We have number of atoms. We have the K. If we multiply K to number of atoms, we get A, which is the radioactivity. So A is gonna be K multiplied N. So A will be K, we have it 7.04 multiply 10 to the power of minus 7 decay, even divide by atom multiply second multiply number of atoms, 2.70 multiply 10 to the power of 15 atoms. Atoms by atom cancel, so we get A equal to 1.90 multiply 10 to the power of 9 decade divided by second. 1 decade event per second is equal to BQ. So A is equal to 1.90 multiply 10 to the power of 9 BQ. A equal to 1.90 multiply 10 to the power of 9 decade. Decade events, or we can go with here. Also, we can go with the BQ. So I'm gonna use the BQ this time. Let's go with the BQ. And 3.70 multiply 10 to the power of 10 BQ equal to 1 Curie. So BQ by BQ got cancelled, and A is gonna be equal to we get 0.05114 Curie. Okay. I hope this lecture was useful, and wish you a great time, guys. Thank you.